let's do some math for fun, and here, if possible, we are going to find integers a, b, c so that a squared plus b squared is equal to 4c plus 3. And as always, please pause the video and try this first. Okay, how did you guys do this? Well, let me show you guys my solution right here. And of course, you should share your solution with us as well. Just leave a comment down below. But anyway, I will show you guys my observations that I'm making along the way. First of all, we do have a sum of two squares on the left-hand side. So that means this is always going to be greater than or equal to 0, right? So with that being said, c has to be bigger than 0 as well. Because imagine if c is equal to -1, then you get 4 times -1, which is -4 plus 3 is -1. And you'll get a contradiction, right? Because it's not possible for you to have a squared plus b squared is equal to -1 when a and b are just integers, right? So it's not possible. But the truth is that it doesn't really matter if a, b, c are positive or negative, right? So that's kind of the out of the consideration. But anyway, let's take a look at the following. Notice that 4 times c, this right here is always even. And when you add 3 to that, the right-hand side is always odd. Sometimes you have to be aware of the even and oddness, okay? The evenness and the oddness. And there's a little proof by the Simpsons. He claimed that he found a counterexample to the Fermat's last theorem, right? But he can easily disprove his counterexample by using the even oddness. Anyway, here is what we are going to observe. I will just write down, okay, we know 4c plus 3 is odd, and let me just write down all the steps. If you want to write down your solution, this is what you will do. I'll just say, since we notice that 4c plus 3 is always odd, so the right hand side is always odd. What does that mean? Well, when you have one thing plus the other being an odd number, you must have one of them being even and the other one being odd, right? Because even plus odd, it's odd, right? Well, these are just squares of a and b. If you have an even number, you square that, you get even. If you have an odd number squared, you get odd. Okay? And if you have a squared being even, a has to be even. And for example, if a squared is odd, then that means a is odd. Okay? So they go like back to back. But anyway, we know that the right-hand side is odd. That means either this or that is odd and the other is even. Okay? That must be true. And once again, we are just going to write down what we just said. So we are just going to say that we must have one of the a or b to be even. And once again, I'm just saying a and b, okay? Because once again, when you have a squared, it's even. That means a is even. When you have a is even, that means a squared is even. So they go back to back. And we just want to talk about a and b like this. But anyway, I'm saying that either a or b has to be even, and the other one has to be odd. Okay, so that's the idea. And now, this is what we can do. And this is one of the abbreviations that if you guys haven't seen in the past. This is the coolest logarithm. No, just a joke. I will just say without loss of generality, okay, W log. This stands for without loss of generality. And what this is doing is that, well, you don't need to worry about you pick a to be even or b to be even because it's either a or b, right? So it doesn't really matter. So I'll just say without loss of generality, let's say let's just say a is even and b is odd, okay? And seriously, you can just change the a and b. Right? You can say a is odd and then b is even. That doesn't really matter, but you do put this down so that it can be legit. Okay, so now you know a is even and b is odd based on what we are saying, right? We may write, when we have an even number, we can say a is equal to 2 times some other integer. I'll just put on k for that. And because b is odd, we can say b is equal to 2 times another integer. It doesn't have to be the same as k, so we just put on l, but at the end, you put down plus 1, okay? So this is the form for even number, and this is the form for the odd number. And I will just say for L and K, be in the integers. This is like a horrible Z, sorry. But anyway, just like this, okay? So L and K are integers. Now we have an expression for A and B. This is what we can do. Of course, we can just plugging this back into the original equation. So we know that A squared plus B squared now, this will be, okay, A is 2K, not like the 2K18 for the basketball games, but 2K, and then B is 2L plus 1. So we just add plus 2L plus 1, okay? And now we can just do some algebra. 2K squared is of course just 4K squared, and then when you multiply this out, you get 4L squared plus 4L plus 1. And here's the part that you have to kind of just pay attention to. Well, notice that the first three terms that we have right here, they all have 4 times, right? So you can factor out the 4. So let's do that. This is 4, parentheses, and we have K squared plus L squared, and then plus L like this. And then we have the plus 1 after that. And now, take a look. K and L are integer. So right here, this must be an integer, right? So when you have A squared plus B squared, notice the form has to be 4 times the integer and then plus 1. But on the right hand side, this is saying A squared plus B squared, the form has to be 4C plus 3, right? 4 times the integer plus 3. And this is the contradiction. So what we can do is, I can just tell you this right here, which is never possible to be 4C plus 3, right? Because once again, you can also use modulo arithmetic if you want, okay? So if you want to do that, you can say the following right here. Another way to write it, you can say that A squared plus B squared, this right here is congruent to 1 mod 4, because this part is the multiple of 4, and then when you divide this by 4, you get a remainder of 1, right? So you can say this is congruent to 1 mod 4, but when you have 4C plus 3, this right here is of course congruent to 3 when you mod 4, right? So that's why I said this right here, it's never possible to be the same as 4C plus 3, right? When you are talking about just integer solutions. So the idea of all this is that this is actually not possible. I'll just say to you guys that thus, let me just write down. We conclude that the equation A squared plus B squared is equal to 4C plus 3 has no technically it's integral solution, but I don't really understand why people say integral, because integral means integral, but you know what I mean. I would just say no integers solutions, right? Yeah, so this is how you can do like an argument. Oops, I put a box the wrong way. But yeah, I should put a box like this. But yeah, hopefully you guys are okay with that. But anyway, I just want to show you guys like a style of like doing some numbers to prove or disprove, right? Yeah, this is one of the things I really like when I was in school. But anyway, hopefully you guys all like this. And if you guys are new to my channel, please subscribe. I like to make lots of math videos for you guys. And as always, that's it. Okay, before we go, here's the bonus part. Is this true or false? This is false. It seems like to be a counterexample to the Fermat's law theorem, right? But no, just no. Why? If you look at the left-hand side here, this right here, well, it's an even number raised to a 12th power. This right here is even, right? And you see that this number, of course, the answer is 1, so this is odd. And when you raise that to a 12th power, this right here is odd. But on the right-hand side, this is an even number. When you raise that to a 12th power, you end up with even. And what we're saying is that when you have an even plus an odd number, this is equal to even. Of course, this right here is false, right? So keep this in mind. This is a pretty good strategy to try to show an equation has integer solution or not.